Alright, so in this lesson we are talking about inverse matrices in order to solve a linear system of equations. Remember, one of the applications, the main application, at least for this chapter, for matrices is all about systems of equations. So we'll see that definitely in this lesson. So our objectives, there are three of them. The first one, to find the inverse of a square matrix. Now we've talked about this word inverse before, and inverse in mathematics means something that undoes something else, like the inverse of, say, dividing is multiplying, something like that. The second objective, we're going to solve a matrix equation using inverses, which is like the title of this lesson, and then actually apply it on objective 3 to solving a linear system of equations, which is what we did in like Kramer's rule, but you might even like this method even better. Let's see. Okay, so I'm going to start off with a warm-up question. I know you might think this is a very bizarre picture, but imagine you lived in a strange world that never defines subtraction or division. So what would you do in order to get the same results? So if I wanted to, let's say, subtract two numbers, but there was no such thing as subtraction, how could I get around that? Same thing with, how could I get around the fact that there was no division? Well, really, these two things don't exist anyway. Subtraction is the same thing as adding a negative. It's adding an inverse, okay? And division is, well, that doesn't exist either. It is the same thing as multiplying by a reciprocal. Again, it is inverses. And in terms of matrix multiplication, there is no such thing as division. So what we will have to do is multiply by an inverse. So let me explain the picture here for a second. So one of the creation myths that humans on this planet have come up with is that, of course, the Earth was a flat disk, and, well, what was holding up that flat disk? Well, it was 5 elephants. Well, what were the 5 elephants standing on? Oh, of course, well, they were standing on a giant tortoise. There you go. That's where that picture comes from. Okay, so our first objective, being able to find inverse of a square matrix, and the picture here, like this jungle gym thing, looks like it's a lot of fun. And to me, it looks like maybe some sort of inverted square, which is what we're trying to do. Now, you might judge just by that objective that we can only find the inverse of square matrices, and that's going to be true. Okay, so let me just rewind for a little bit and talk about our identity matrix. The identity matrix is like the number 1, right? If we multiply the identity matrix by any other matrix, we get that matrix back, okay? For a 2 by 2, you have 1s along the main diagonal, 0s everywhere. Well, that's how you make any kind of identity matrix. They got to be squares, 1s along the main diagonal, 0 everywhere else. And this is what we were saying before, that if you multiply a matrix times times the identity, you always get that matrix back. Okay, so knowing that, let's multiply these two matrices together. We're going to find the product AB, and they're both 2 by 2, so I know that I can do the multiplication. So let's just go ahead and write these two things down. -3, -4, -1, -2, and I'm going to multiply it times, there's fractions in it, oh my gosh, what are we going to do? -1, 2, a half, and -3 halves. Okay. So when I multiply, remember it is a row times a column, then I'm going to add those things up. So -1 times -3 times -1 is 3, plus -4 times a half is -2. Okay. That's just going to be the number 1. And then going on from the first row to the second column, -3 times 2 is -6, plus -4 times -3 halves. 2 goes into the 4, 2 times 3 is 6, +6. Hey, that's the number 0. This has turned out to be pretty easy. Okay, even though it has fractions in it. Now moving on to the second row, -1 times -1 is a +1. -2 times a half is a -1. Hey, that's 0 also. Okay. And finally, -1 times 2 is a -2. and negative 2 times a negative 3 halves. The 2 goes into the 2 one time. They basically cancel out, leaving me with a positive 3. Oh, and that's the number 1. Hey, look what we just got back. We got the identity matrix. Okay, so we multiplied A and B together, and we got the identity matrix back. What kind, what's the relationship then between A and B? Well, they must be inverses of each other. Like, for example, if I were to multiply, where'd my pen go? 5 times 1/5, I get 1 back, right? These things were inverses of each other, just like these two matrices are inverses of each other. So inverse of a square matrix A is another square matrix such that whenever you multiply them together, you get the identity matrix. And look, notice that it goes both directions. Commutative property does work with inverse matrices. A times B gives us the identity matrix. B times A gives us the identity matrix. Okay? In terms of notation, we denote the inverse of a matrix with A to the little negative 1 power. Okay? That's what we use for the inverse of a matrix. And then, whoa, hey, you just stalled on me. The inverse, of course, only defined for a square matrix, but even more than that, its determinant cannot be 0. The determinant of that square matrix can't be 0. If it is 0, you cannot find the inverse. It's called invertible. It's an non-invertible. That's what it is, a non-invertible matrix. Okay. So let's find the determinant of A and see what the relationship between the determinant of A and these two matrices. These are the same ones from exercise 1. The ones that we saw were inverses of each other. So I know a determinant. That is super easy to find. I just cross multiply here. So here I get negative 3 times negative 2 gives me 6 minus negative 1 times negative 4 is a positive 2. No, it's not. It's a positive 4, which gives me an answer of 2. Okay. So now look at the original matrix. Here, let me erase all these markings here. Erase all the markings. There we go. The original matrix, this 2, and the new one. Do you see any kind of relationship between them? Anything? Well, look at this. You got 2 and 2 on the bottom of these fractions. It's like something's been divided by 2, right? And some of the same number, like this negative 1 is in here, negative 1 is in there. This 3 is in there, the 3, negative 3 divided by 2. I wonder if there is some kind of relationship between all of those things. Well, there is. Let's see it right here. Here's the definition of the inverse of a 2 by 2 matrix. Okay, so let's assume we have a 2 by 2 matrix that just has A, B, C, D in it. To find its inverse, look what I have to do. I have to take 1 divided by the determinant of the original matrix. This is why if the determinant of the matrix is 0, you can't find the inverse, because you have to multiply this as a scalar through the matrix. Now let's look at how the new matrix is formed right here. Excuse me, the new matrix is formed by, look at this D and this A. Where did the D and the A come from originally? Well, the D and the A were the same thing as the A and the D from the original one. They just flipped places. Okay? And this, I have a negative B and a negative C. Those are in the same exact places, but they switch signs. Okay? So how I make the inverse of a 2 by 2 matrix is I'm going to flip the ones along the main diagonal, and the ones along the minor diagonal, I'm just going to change their signs. Just going to make them negative. Then I have to divide everything on the inside of the matrix by the determinant of the original matrix. Okay? So let's find the inverse of this 2 by 2 square matrix. Okay. So the first thing that I need to do is I need to find the determinant of this matrix. So 2, 1, 4, 3. Cross multiplying here, I get 6, 6 minus 4, that's 2. Okay? So to find the inverse, I first take 1 over the determinant times, now I've got to scramble up my numbers in my original matrix. These two switch places. So this 3 comes up here, the 2 comes down here. And I have to switch the signs on the 4 and the 1. So negative 4, negative 1. Okay? So now let's just divide everything in the original matrix by 2. So 3 halves, a half of -4, -2, -1 half, -1 half, and then half of that is a 1. So here is the inverse of that original matrix. Okay? If I were to multiply A times this matrix, what would I get? I would get the identity matrix back. Okay? So why don't you give this a try on exercise 4. Pause the video, find the inverse of that square matrix. Well, do you have a lot of fractions in yours? Because you should have. So here's what it looks like. You find the determinant first, and the determinant turns out to be 22, which means I'm going to have to divide everything in my matrix by 22. Okay, so that's right up front here. And then I take my original matrix and I switch the 2 elements on the major diagonal, and then I switch the signs of the ones on the minor diagonal. And then I'm just going to distribute that that 122 throughout the matrix, and then I just reduce the fractions, you know, make it look a little bit better. Okay, so that's it on finding the inverse of the square matrix.